And welcome to the folk on Zoom as well. Last year with 2020, we developed a virtual capability, so we're excited to share this hybrid show with you. My name's Allison. This is Sarah Brown. We've been the ones behind emails and a lot of the organization, and thank you again for coming here and supporting the art show. This year, we're also collaborating with the Interstellar Research Group Symposium, who we have a mix tonight from attendees, supporting artists, yes. Artists that have submitted to the show and a lot of previous artists as well. And then we, of course, have to thank our Galileo Circle. They have supported us many years for the alcohol and the food. Thank you, Galileo Circle. It's the kind of the donation hub for the College of Science. And so when you donate to the College of Science, eventually it trickles down to the Lunar and Planetary Lab. We'll talk about some donating to the Lunar and Planetary Lab a little bit more specifically, but I'd like to introduce Stephen Fleming, who is the organizing chair for the Interstellar Research Group, or another acronym for you, the IRG.
We do love our acronyms. Thanks for coming, everybody. Stephen Fleming with IRG. My day job is here at University of Arizona, actually right across the mall. For those of you who don't know, the timing of this was triggered by an event that turned out not to happen. NASA has their advanced technology group. It's called NIAC, NASA Institute for Advanced Concepts. And they, every year, bring together about 150 of their more far out researchers to swap ideas. And that moves around the country. And it was going to be here last year. And then it wasn't. And then it was going to be here this year. And we, the Interstellar Research Group, every other year run a conference talking about many of the concepts involved in building interstellar probes and eventually interstellar spacecraft to take humans. And that's everything from life support to propulsion to ethics to you name it. And we thought, wouldn't it be a great idea to have the NASA NIAC event in Tucson and then the Interstellar Research Group event in Tucson be adjacent and have some cross-fertilization between them. And oh, by the way, that's the same weekend that Allison and Zara were going to be putting together the art show. So why don't we throw a big reception on the Thursday night, which is the end of the NIAC program and the beginning of the Interstellar Research Group, and that's kind of the handoff from one to the other. That was the plan. Then Delta variant. And then about 3 weeks ago, NASA pulled the plug on their in-person event here in Tucson. So that was purely virtual. It just finished about 3 hours ago. And it was great, but it was Zoom. And so the 150 researchers that were going to be here in town, most of them didn't show up. But we're still having a great evening tonight. I think we've got a good group. This is a good intersection. You've got the honest to goodness researchers who are doing the science. You've got engineers who are building products based on that science. And then you've got the artists and the liberal and the other liberal arts folks who are, looking at that from a different perspective and doing something else with it. And that's really cool. And that's one of the great things about University of Arizona, is we do all of those things. We do very hardcore science, we do great art, we do everything in between. So with that, we're thrilled that you're here. If you're not aware, the actual conference for Interstellar Research Group starts tomorrow over at Marriott. I'll still sell you a badge, but it's going to be handwritten at this point. And would love to have you involved in any of the events there. We do have a free event on Sunday evening, right after the it's Sci-Fi Sunday. Is that right? At the end of Sci-Fi Sunday here, walk over to the Marriott, and we're having a public free outreach event, which I think a lot of you might find interesting. Marriott, 6 o'clock to 8 o'clock. Great. Thanks, Alice. Appreciate it.
Okay, and just a few considerations. Again, hello to our folk that are virtual. So this is Zoom roomed. So there are microphones across the whole back. And so to keep the chatter down for the folk on Zoom, just make sure that we're not making too much loud noise. Essentially where the large squares with the green light is where our microphones are, which means when you ask questions at the end, we'll hold questions until the very end. You can just ask them This mic is also projected out into the atrium. If you do need to go out and use the restroom and come back in, hopefully you can still hear what's going on, but just be mindful as this room is quite sensitive now with new technology. The university had to update the classrooms with that, which is pretty cool. So we've got some new capability there. And as I mentioned, we'll hold all questions till the end. That goes for the folk on Zoom, although our folk on Zoom can just enter them in the chat. We'll be monitoring them, but answering at the end. And so next, I would like to introduce our speaker for the evening, who is also a professor here at the Lunar and Planetary Lab. Dr. Christopher Hamilton's just returned back from several months of investigating the active volcanoes in Iceland. And well, that was not the transition we wanted. Thought I deleted those, but I'll fix that in a moment. And his research focuses on planetary surfaces and analogs, and he's been on this sabbatical for several months, and he's going to be talking and showing us the footage from these active volcanoes. And I'll go ahead and invite Christopher Hamilton up to the stage.
We'll start with the microphone test. Sounds good in the back too. All right. Fantastic. So just before I start with the main presentation, I just wanted to introduce Iceland and a touch of why this has been such an important part of my life. I actually first went to Iceland as an exchange student, visiting Reykjavik, the capital, in 2002. And really just fell in love with the country, with the people, with the process of being able to explore this really unique volcanic landscape as an analog for Mars and other planets. By that, we mean we can go to this place and study the volcanoes and understand the processes, and even test instrumentation to be able to gain an understanding of how we can understand, interpret, model, and even explore similar terrains on Mars, on the moon, Jupiter's moon, Io, these volcanic environments all throughout the solar system. So after spending time there and finishing up, I did my PhD at the University of Hawaii, studying Kilauea. And as much as I love Hawaii, Iceland is my favorite. So for my sabbatical, I had a chance to be able to spend a year there with the Fulbright program. It was a little delayed, so I wasn't able to start in September. I instead got there in January. Terrible month of the year to get there. Completely dark, jet lag going through Frankfurt, everything is in lockdown. And it was just in some ways pretty miserable until we started to have a series of earthquakes. And not just a few, tens of thousands of earthquakes larger than magnitude 3. We're feeling them all the time in Reykjavik. And in fact, before the end of the eruption, hasn't actually ended yet, but the period of peak seismic activity, there were over 50,000 earthquakes, many of which were even over magnitude 5. And we felt them because the earthquakes were happening here on the Reykjanes Peninsula, maybe 45 minutes from the airport, a little over an hour from Reykjavik, and actually a part of Iceland that's very rugged and underexplored. And people hadn't really thought about it as being a particularly important site for new eruptions, even though the most recent eruptions have occurred 800 years ago. That was 800 years ago. And so people have been thinking about these other places. It was here, there's a big eruption in Holafjörn near Askja. These are the areas in the highlands that people were really focusing on. And so there was this fantastic transition from these regular seismic events, these earthquakes, to a particular type of seismic signal called a tremor. And that means the movement of magma is taking place under the surface. So that took place. First earthquakes were around February 20th. First tremor was on March 3rd. The University of Arizona was fantastic, helped to be able to provide some funding through the Research Innovation Impact Fund to get our equipment from the lab upstairs to Iceland right away. The National Science Foundation, 4 days before the eruption, approved our rapid grants to be able to study the eruption. And for the 5 months after that, we were able to explore this volcano over and over again. I had no idea how long it was going to last and didn't want to waste a day. So the main presentation, we can go to the movie. So I did a lot of drone flights. I mean, over 500 drone flights. I went to the volcano somewhere between 80 and 90 times, and did my best to be able to document scientific observations about different processes related to lava flow dynamics and astrobiology, but also just try to take, just wait a second before starting. but also to try and document visually how the eruption was unfolding, because there's so many details with an eruption, you can get overwhelmed. And so if you try to focus on each little thing, then you can miss the big picture. So every day I try to take a lot of video footage, and this is actually my first attempt ever at making a movie. It's been a crash course in Adobe Premiere all week. So this is the first cut, and I'll just have a conversation as we go and share a little bit about how this really unique eruption unfolded for the first 5 months. Okay, so this is a picture from the very first day. We came in with the Coast Guard, helicopters are going, people are walking out, a complete zoo. And so we were able to get there at the very beginning. But in fact, we've been there before the eruption started. So beginning in March, we were going out to every one of the little valleys that could be potentially inundated, collecting samples, measuring the topography, trying to get the best possible idea of what the landscape was like, both physically and also what was living in all of these little environments. So these areas are all glacial deposits and haven't been modified since the end of the last glaciation. But we knew the lava would come out through those valleys. And this is where the eruption actually began, in Geldingadaler, and then flowing out into these areas towards the sea. And so we were able to go out from the very beginning and begin to get the drone up in the air. And in the beginning, the volcano was so small and so cute. Great. And so you saw a little line of people in the background. Everybody from Iceland came out of hibernation. There were up to 10,000 people coming out to this volcano. This little line of people coming out, rain or shine, or mainly snow at this time. And we were able to get the drone in the air and see what was happening. Now, throughout the presentation, I will, if the video is sped up, and include a little note there. This is 10 times playback speed, so you can see the lava moving a little bit more quickly. This is another drone image looking straight down. You can see these two vents that both opened on March 19th at 8:45 p.m. and continued well into April, feeding lava into the system. Now, this is a graduate student, Joanna Voigt. She was fantastic and came out really early on in April, and she had a fantastic show. So that first fissure opened up, as I mentioned, on March 19th. And so this is this is April 5th, just a couple of days after Joanna arrived, and a new fissure opened up. We were on our way there, the fissure opened, they blocked us, we just had fish and chips, and then in the evening went out and had a chance to be able to capture this really phenomenal perspective. So these are some of the vehicles. We've got ours down there on the edge. And using the drone, we could begin to get a survey of the area and see where this particular valley, Miradalur, which is one of the 4 valleys in the area, was being inundated by the lava that was coming from this upper spot. And it was just absolutely spectacular. So we kept going back every day. And so this is what Fissure 2 looked like. So this is the one that opened, as mentioned, on April 5th. And it's feeding this wonderful series of lava flows down, not into Geldingadaler like the first event, which was still active at the same time, but this time towards the more northeasterly valley, Miradalur. And so absolutely hypnotic in terms of being able to watch the lava flow from this plateau, then down into this valley. It's a really very, very steep. And so you could see these fantastic lava flows. The snow was there, very few people the next day. And you can see just between those 2 days how much of an advance you had with the lava coming down. Now, I actually thought this area would be quite safe from future inundation. And so we actually began setting up astrobiology sites where we wanted to see what types of microbes would be potentially colonizing the lava flow, going back every week during this entire time period to see what the first microorganisms are and how these populations changed. So we had a couple of sites around the edge, and they actually were very well preserved into June, and then we moved to another sample site. And so you can see the lava very fast moving that was in real time flowing down into the valley. So this is a little bit later, basically still all in April. This is Fissure 2 sitting there. And then this was another fissure that opened just a couple of days later. That was on the 9th. And already it was a very small volcano and it looked like maybe it wasn't too active, but you send the drone over the top and you can see it's just smoldering inside. The gases are coming out and it's feeding a lot of lava actually through a lava tube system. And this was then that first very cute volcano that we saw in Geldingadaler. So it's now been erupting for almost a month. It's focused into 2 vents and it's really becoming a bit of a monster, but it actually won't be the key event that tells most of the story. but for the first part it was. So these beautiful lava flows, kind of sluggish at this point coming out. But as I was flying these drones every day, I was getting a little bit more brave about what I'd be willing to do. So I was like, hey, it seems pretty good. I can do it. I can fly over it. And so I was like, yes, that's great. And so I was like, what happens if I just go right over? And so it was a really hypnotic process. I'm just sort of looking into the eye of Sauron here, with this bubbling pot. And so the snow is blowing and it's just, you're outside and you're sort of in this really weird virtual environment, looking at your controller and trying to gauge where you are. Joanna is a fantastic spotter. She did a lot of controlled flights as well. And the eruption just kept getting better. So this is 10 times speed. You can see this almost artery-like flow of lava coming out from the vent. It was really, really pretty spectacular. This is what's called an flow. And so again, at 10 times speed, this is now back into Miradollar. We're feverishly setting up little markers everywhere so that we can geo-encode or check distances when we're looking at these different flows. And so this became a really nice one. And then we were really lucky and had more help. So Michael Christopherson came out. Fantastic. Having 3 people made such a big difference. And so we had this drone for another project that we're working on. And Michael, who is interested in having a ground penetrating radar. And we thought, well, let's put these 2 together and try doing something nobody has done before. And that's an image active lava channel using GPR. So these are some of our little markers that we'll put out 60 of them. They're littered all throughout, but they're critical for actually measuring these distances. So there's the little drone. So I'm setting up this other one because the main drone doesn't have a camera. And so what I want to do is be able to get above it and then be able to see exactly where it is beneath. And so this is in real time. In a moment, it's going to go out of the field of view. And we're going to speed up to 10 times and go through this weird Frogger exercise of trying to get it to be able to go over and give the cues for when we're getting to the edge of the lava, where's a good place? Okay, we're gonna start. And across we go and to the other side of the lava flow field. And then we're gonna turn around. Now we've got a good route and we're gonna come right across and be able to make measurements using this ground penetrating radar. So that was the first time. We're still working to see whether or not it was particularly meaningful. Lava is not the best radar reflector, especially if it's molten, but we just wanted to try it out. And so that's kind of the experience you have when you can go back day after day and just try new experiments over and over. So now we're into May and the eruption has changed. This is actually not our little cute volcano that was there in the beginning. It's just over the hill and almost completely buried. This is a new fissure that opened a little bit later on April 13th. And in fact, there were 2 little fissures. They circularized into this main one. And for May and into June, it was in this fountaining phase, just these fantastic, in some instances, up to 600 meters high, these fountains. And so we actually ended up walking there sometimes and being able to have lots of ground-based video footage. And when these tall fountains, with the higher ones, would probably get up to here, and in some cases, 600 meters would be about there. Just your skin would dry out, your eyes, everything. You're standing there, and you just have this wave of heat that comes in. And at that point, the eruptions were happening basically every 9 minutes, like clockwork. And so, finally, during this period in May, the lava made it down into a new valley. That was the one that I showed you in the very beginning. That's called Natai. And so the lava finally started to go into this last valley. That's the last section before you get to the coast. And people were concerned about this road being cut off, but also by the fiber optic cable that supplied internet to most of Southern Iceland. So they really protected those pretty well. And so this is out to sort of the edge of where the flow was in Natai. And they ended up building some dams here, which have held for the time being, but eventually the lava will reach the sea. So one of the really nice things at the end, mid-May, was that an undergraduate student, Alexia Kulis, you just saw there, she came out and really fantastic. So we had help. And this is Solange de Hamel. She was in MCD, and we were working on our astrobiology project. So Alexia was fantastic and stayed into June. And then in July, we had new reinforcements. This is another graduate student, Nathan Hadland. And so we were interested in not just continuing this astrobiology sampling on a regular interval, but to compare it to what was happening in the broader surroundings. And so we were interested in sampling these older lava flows. That one's about 2,000 years old, and just see how the microbial succession develops over time. So during July, the eruption just kept going, building up this bigger and bigger cone, and just this boiling pot sending out these waves of lava, absolutely spectacular. And so this is in late July, getting a little bit taller, the sides are getting a little bit steeper, and there was a breach. We actually just captured it in this footage. And so this whole area, while we were there, collapsed. And it was just wild. Instead of feeding out these little flows into Natai, the lava flow breached through the side and started going back towards Mirador. And we happened to be lucky. We're there with the BBC film crew that day, and they were really happy. It was just wild. So our sampling sites down there had been buried, but it's okay. We'd already moved them up to a higher site near Fisher 2, which was the highest topography and wasn't buried. So this is the same day, just a couple of hours later now. And so you can see all these rivers of lava are pouring over all these different surfaces. These hills that used to be giant beasts that we would be afraid to climb up are almost all completely buried and then flowing in and just the coup de grace in terms of our earlier sample sites. So this was a really beautiful time of the eruption. Now that this breach had taken place, it was flowing lava into Mirador. We had a number of different aerosol samplers to see what was moving around. We had time-lapse cameras that were there, but still just did these drone flights to be able to see what was happening. And one evening, I was there with Nathan, flew out and saw this. It's just absolutely wild. So that's one of our little markers. It's a meter across. And from above, you can see the lava is jumping. It's literally a fountain that's actually then cooling underneath. Just absolutely wild. And we have some instances we actually saw a dust devil go over the lava channel and create a lava tornado. But those lights are pretty far away. We're over 3 kilometers flying. And so every time we land safely on one of those longer flights, there's definitely a sigh of relief. So this is in August, and it's basically a mess. So that's building $1. It's basically completely filled. Natai is down there. The valley with no name. It's not really a valley anymore. And Mirador, our friend over here, it's almost breached out on that side. It's almost breached out on that side. It's almost breached out on this side. It's just filling this whole landscape in a process that I've referred to as fill and spill. It's actually quite similar to what happens for large lava flows on Mars as well. So August was my last month there, and I tried to get out as many times as I could. These really beautiful rivulets of lava coming from the main vent, which is just still spilling away and making a mess. Every day getting a little closer to burying our last astrobiology sites. This is at 10 times speed, and you can just see it pumping like a heart and putting the lava all through this lava channel system. And then one really interesting day, just saw that it was really gassy. Sent out the drone. I was like, well, what's going on here? This is just really weird. And so peered down, and this was actually one of the more terrifying moments. It's empty, completely empty, over 100 meters down. Usually these things would collapse and you wouldn't see it. The next day, went back out to see what was going on. It's pumping again. It doesn't care. Basically putting out, making a mess again. But it was so bizarre to look down at this very familiar volcano, and it just shut off. It was empty. It was really, really bizarre. And so the next day, went back out, and it was empty again, and just drained. And this was really an interesting period, but unfortunately, it was my last day in the field. So the eruption is still ongoing. It's sort of in this on and off mode at the moment. And we just had this fantastic opportunity to be able to bring out quite a few students, undergraduate students, graduate students, and staff scientists, and definitely very thankful to a number of other sponsors. So happy to answer as many questions as people would like. I think we have another slide as well.
We're going to facilitate questions both from the webinar and in the room, and I'll transition to a display slide in the back. Let's go ahead and start within the room here. We'll go front row, middle row, and then in the back here. So right here in the front.
Are
Okay, an excellent question. So for everyone, the question was, am I going back to Iceland? Iceland is really one of my homes. I plan to go back every year if I can for the rest of my life. We have actually a really big project at the moment to be able to test rovers and drones for a next generation Mars missions, much like Perseverance and Ingenuity, but actually a future dedicated mission with samplers and many different robotic systems. And we'll be testing those in Iceland. And so we'll be going back next year, and we'll be going back hopefully every year that I can. It's a really wild and changing landscape.
Okay, and then I think I saw, was it the gentleman in the blue? We'll come back to you, Stephen. Yes, right here.
What did you learn from the ground penetrating radar?
So we did an initial post-processing. One of the other things we have to do is build a full three-dimensional digital terrain model to be able to see whether or not potential reflectors are basically echoes of some of the features. And basically, in terms of radar, the liquid, just like water would be, it absorbs the radar signal very quickly. But we do see a faint signal that should suggest that we might be able to catch a little bit of the edges. But one of the key things we're going to need to do is to be able to work through these data, make it a three-dimensional model, do what's called a clutter simulation to be able to see what echoes would be generated just by the topography to know if what we're seeing is real. But certainly one of the things that we were able to do is also image some of the lobes and see where we could get a signal and where it drops out. And where it drops out, we think that's where the molten core is. So it isn't necessarily that we're seeing the lava channel, but what we're seeing is that the attenuation of the radar signal where we have molten lava, and that might actually let us figure out where you have molten pathways inside. So it was a first attempt, but it's a bit of a null result. But the key thing is lava is very radar absorbent, and so we aren't getting a good reflection, but that actually can work in our favor if we construct the right experiment.
Okay, and I believe I saw one in one of the back rows. Yep.
Yes, so I have a pragmatic question. Are there best practices or following your expert judgment for how you approach a lava flow like this?
Yeah, no, this is a very, very good question. This eruption has some advantages and disadvantages. One advantage is it's very accessible. That is also the disadvantage. So the lava erupted in a valley, so you could just walk around all of these hills, and it was really pretty close to the road. We had access to be able to drive in, but you could walk in within a couple of hours, and most people did. And so being above the lava actually helped quite a bit. And Iceland was very good about being able to do a lot of gas monitoring, letting people know when the wind speeds were going to be a potential risk, whether or not wind direction was going to move gases in a place. And so they kind of managed where people would go. The gases are probably the biggest threat. The lava is a little bit sluggish, and here it was kind of contained. But this isn't a general characteristic. Most lava flows aren't contained by mountains very neatly. This was what's referred to in Iceland as a tourist eruption. Basically, it was volcano Disneyland. It's not representative of what most eruptions would be like. This was a very low volume or low fusion rate eruption, varied between about 5 and 10 cubic meters per second, which in the world of volcanoes is really small. And it was topographically confined. It occurred in an area where there was no infrastructure except this cable, which people were able to reinforce by burying. There were no people that lived there. It's actually, there are a couple of shepherds would overnight. In fact, Natai is the overnighting place for sheep. The Geldingadeller is the valley for the gelding horses and for sheep. This has been used a little bit for grazing, but nobody was occupied, nobody was harmed. That's the trouble with volcanoes. You can't hope for a volcanic eruption. You can't hope for a volcano like Vesuvius or Katla to erupt. This was really a perfect one, and so it was approachable. So in general, what to be able to do, don't walk on the lava, make careful observations, wear a mask. We also had gas meters because it's really the gases that are the most dangerous. And the second most dangerous in Iceland is the weather. If it snows and you have a whiteout, sometimes we get hail that just landed, and all of a sudden there was just a fog that was coming off the surface and you had no visibility. So having a good communication plan, those are all important. But basically, if you don't step on the lava, you can get pretty close, and some people were barbecuing things and having a great time.
We'll do Stephen Fleming, then we'll go to the webinar, and then we'll come back to you, sir.
You mentioned twice now a fiber cable, and I think you mentioned a road that needed to be protected. How do you protect against that?
There were a couple of tests. This, because it was kind of a tourist eruption, it was also a science eruption. So a lot of the drone observations we were doing were to do things like measuring exactly what the topography was like. Then they'd come out with an excavator, they'd dig a trench, they'd put down some basically test fiber optic, they'd put down different insulating materials, wait for the lava to go over, measure how it was doing. It's like, okay, that one worked pretty well, that one didn't, we'll build the next barrier. There's no way to stop it if it keeps erupting. It'll flow over. This is not the main road from the airport in Keflavik to Reykjavik. It's a smaller road. There's a fiber optic cable. There's one house that could potentially be affected near the coast. You can't stop it, but you can learn from it. But the only thing that will prevent it from reaching the road is just that the eruption stops.
Okay, let's check with our webinar folk. Zara, do we have any questions online? You can read them out loud.
Hi, Allie. Yeah, I'm looking at our attendees, and it doesn't look like anyone has a question. Does anyone have a question? I'll give you another moment to respond. No, I don't think we have any questions from the webinar.
Okay, and then let's go to this gentleman right here. Thank you, Zara.
Where did the lava go that was missing from the crater? Because it didn't look like there was breakthrough or not. Did it just go down in the lava tubes and drain? Or?
Yeah, so this is a very good question. And we did go back a couple of times because the second time we were really pretty prepared, and we could see in the seismic data if there was an elevated low frequency tremor that let us know that there was gas moving through the system that was then creating basically these bubble bursts that we could detect. When that shuts off, we can see a drop in the seismic signal. We wanted to see what happened at the vent. And what happens is a lot of gas comes out. And what's really kind of bizarre about magma when it's that close to the surface is almost all of it's gas. So once you stop the tap, the gas that's in there might be 70 or even 80% of the volume. It just basically collapsed like a souffle. The gas came out and the whole thing dropped down. And in fact, in that last little video, it was maybe obscured by some of the acknowledgements, but you could actually see there was a little bit of a glow in the bottom. And basically the gas, the bubbles popped, the whole thing dropped down. I think the 100 meters must have, based on our constraints for that second day, have completely drained within less than 20 minutes. So it's a very rapid process.
Let's see, yeah, in the front row, and then we'll go back to the further rows, but yeah, right here.
How much lava did the lava dam stop?
Well, the first two that were set above Natai, they probably bought about a week. So they did work, they did stop the lava, and then it went into a different valley, but it probably provided a little bit of a week. The good news is if you set up some of these dams, you'll never be able to stop it completely, but you can get time. So you could provide in this particular instance, because everything's funneled through these small valleys, you could provide the time that people need. And so just as a safety, there are a couple of dams that have been set up. So they would give you time, which can really make a tremendous difference in terms of the security of the people living there. You know, they're not terrified their house is going to burn down right away. You know, it's still heartbreaking to be able to see this zombie-like lava flow marching its way towards your house, but it can give you a little bit of time.
Also, what did the lava tornado?
Yeah. So the video that I showed was all from one drone. It was a Mavic 2. We actually used probably 6 different drones that had ground-based images. I could make a larger movie, but the video we had was from the ground-based one. And so it basically looked like a little dust-up, a little tornado that was coming over, and then it crossed over onto the lava, and all of a sudden sucked the lava up like a water spout would, and started to fling large chunks, maybe up to a meter or two across, these plates of lava out maybe 100 or 150 meters, so over the distance of a football field. So I've seen these before, and you've probably been in a dust devil before, and you feel a little spray of sand. I had no idea that they could cast like these frisbees, these chunks of lava crust from the top. So it was pretty wild, actually. There were only a few people there, fortunately, but basically just sucked up the lava from the channel and started flinging the pieces. It was pretty wild.
Let's see, I think I saw 2 questions over here. Yeah, a white shirt here, gentlemen.
So what sort of insights did you gain about bacterial growth from volcanic eruptions?
Yeah, so that's a good question. I can't begin to describe how complicated and how many steps there are. So what you have to do basically, we had series of aerosol samplers that were seeing what was moving around in the area. And then we would go to a number of different sample sites and collect in usually triplicate the different samples that we would then bring back to the lab. And then you have to crush all the samples up into a fine little powder. And then we did two different things. First is you split it to be able to make sure you've got a backup in case anything goes wrong. And you take one part. And then we did a culture experiment. So we made a guess as to what type of media and nutrients these bugs would like to eat, and would do a series of plates to see what would grow. Our real tool is to use DNA analyses to be able to tell exactly what DNA is there, but it doesn't necessarily mean that what was there was alive. It just tells you that the DNA was present. So that's where we're checking with what we have in the air traps to be able to see what's flying around and potentially moving, and checking in the soil what's growing there. But the DNA analyses are really expensive. So this is what's called pilot data. So we collect the data, we get a little bit of information. What we saw is that the first microbes that were growing in culture, which is usually about 2 to 3% of the overall population, were beginning as early as 5 weeks after the lava came to rest and started to cool. But we don't know the complete microbial ecology until we do the DNA analyses. So we'll be putting into NSF for follow-up support to be able to do that. The RAPID project is just 1 year, go collect the data, make it publicly available. But the next step is going to be they're looking at the DNA.
Yep, we'll start here and then we'll go to the back. Yeah, thanks, guys.
With all of the gaseous outtake and the thermal energy that the volcano was putting out, that would have made for pretty rough atmospheric conditions. What was your takeaway on drone handling in those conditions?
Yeah, so that was a good question. I was really impressed by how stable they were. So we were using drones that ranged from little tiny guys you could hold in your hand to some of the larger ones were heavy lift drones that had the capacity to lift 70 pounds. But we were outfitting at the sort of maximum weight allowance there, which is 25 kilograms. And they were all really, really stable. In fact, at one point, we worked with so many different teams. We tried attaching a little gas sampler onto a drone and sending it up into the plume above to be able to sample the gases and see what was inside and outside. And in all the cases, if you're watching the footage of the drone's primary camera without the stabilizing gyro, it's nausea-inducing. It's bouncing around, and you can see in the data sometimes that it's flying and it'll drop half a meter or so. But the gyroscopes are so good for the cameras that you almost can't even tell. But in terms of the overall flight, the biggest concern I had were actually the primary winds. And so I think about them not in knots, but in meters per second. Up to 10 meters per second, I'm comfortable flying. Above 15 meters per second, it just, it'll still be stable, but it can't fight the wind to get back home. And that's where most people, and there were hundreds and hundreds of drones that were lost. People would send out their drone and the wind would be against the drone on the way back, and it would just stall or just drift downwind. You really had to be careful about your approach to make sure that you weren't fighting against the wind, that you were working with the wind to get it back afterwards, or it would stall. So the stability, I was actually really, really impressed.
So we'll take the two more in the back, and then Dr. Hamilton's agreed to answer more one-on-one questions about this slide, but let's do the last two in the back here. Trinica?
So funding, if funding wasn't an issue, what instrument would you like to put on a drone?
Yeah, that's a good question. The instrument that we're actually working on with this new project called Raven, which is the Rover Aerial Vehicle Exploration Network, answers that question. And what I would want on the drone isn't necessarily an instrument, it's a sampler. And so we actually have 3 different sampling technologies we're working on for future Mars missions. One is a claw that can pick up a sample and bring it back to a rover or to a person. The second is a coring drill, where we can actually extract a rock core from the material and bring it back. And the third is something called a powder drill, where you actually generate a powder and suck it into a little tube. And actually powders are used a lot in X-ray diffraction and other techniques. So it's actually the ability to bring a sample back is almost the thing after a camera that I would want most on a drone. And that's one of the things we'll be testing starting next summer.
One more, I believe. Was there one in the further back, or maybe it was just you, sir? Okay, I know I saw 2, but yeah. Okay.
I have a question about, you talked earlier about the earthquakes.
Yeah.
Were you able to determine that any of the earthquakes coincide with the burst of lava?
So there's such a wealth of data in the seismic record. And so almost everything we could see on the surface was in some way tied to what was happening in the subsurface. So in terms of, but it depended on the phase of the eruption and what was dominating at a particular time. So our most useful tool for being able to know if the volcano was active in the period from July and into August was looking at high, low, and medium frequency seismicity from the broadband seismometers. And what we would see is that the high frequencies would dominate in periods of repose, just basically background noise. And then the low frequencies would dominate when the lava was coming towards the surface and when the lava was active. And what we think was happening was that these large bubbles that are driving those sort of heartbeats that we saw in the accelerated motion, it's actually putting energy into the walls of that 100-meter high conduit and maybe a little bit below. And that just sort of shakes like a bell and generates this low frequency seismicity. And so we could tell when it was on by these probably giant bubbles that are moving their way through that system and bursting and putting a lot of energy into the rock. So it ended up being one of our most useful tools, but that's just one of the many ways we're using seismic data to help inform when we would go into the field and what we would do that day.
Oh, one last question.
Did any of your drones get hit by lava bombs?
Yeah, so fortunately, as I ended, none of my drones were harmed. However, there were a lot of casualties. And in fact, and if you guys send me a link afterwards, I can send you a video for the lava tornado and also for this suicide dive that somebody did a little Kickstarter campaign. It's like, I want to get a drone, fly it into the volcano and just film its demise. So there's actually this fantastic footage of the drone flying right into it. And it didn't stop. It was a one-way trip. And so that was the most spectacular ending. But fortunately, none of my drones were affected. I was probably a little bit more cautious. But many drones went down.
We throw spacecraft into gas giants and drones into volcanoes. Any reasons to come to LPL? Yeah, Dr. Hamilton, you want to talk about this slide?
Yeah, so this is an interesting audience, and so I just wanted to be able to explain a little bit about how this process worked. We were able to get a number of students out into the field with support from our department as well as from the university. And one of the key things that we would like to be able to do is bring out basically a full group of LPL graduate students to Iceland. And so we ran a couple of major field trips in the past. We did one to Hawaii in 2014. We saw the Interstellar launch at Cape Canaveral a little bit later. And for each graduate student that's going through the program, it's really fantastic to explore, as we do each semester, the different parts of the Southwest. So we just came back from the Chiricahua National Monument. Each semester we visit somewhere in the Southwest, but sometimes they're just things you can't see in Arizona. You can't see a glacier. And so you can't see an active volcano at the moment either. So one of the things we'd really like to be able to do is bring out a cohort of about 30 students to Iceland. As I said, this is the second home for me, and we do probably 2 weeks of camping trip and visit not just the current eruption or the active that we grade or the products, but actually go around the entire country and into the highlands, visiting some of my favorite places and being able to have an extended opportunity. We probably pair it with a class where people learn about Icelandic geology, plate tectonics, the Mars connection, and then we go into the field and then students would do a report afterwards. And so the big problem for doing anything outside of the Southwest is we have to get on an airplane. It sounds like a crazy thing at the moment, but eventually people will travel on airplanes again. And so to be able to get to Iceland, it would be fantastic if people are interested in helping to support this. Now, one thing that personally, if I were thinking about supporting something, I'd be, well, where's my experience? So one of the things I was thinking about doing, and if people are interested, this is an experiment, would be to do a mini version instead of 2 weeks, 1 week trip for people that would be interested. Worked with Icelanders for a long time. A little fantastic mountain bus. It's about 18 people. That'll be myself and the driver, a relatively small group, to be able to go around Iceland, and sort of have a one-on-one tour going to areas like this, going to Loki, which was one of the largest eruptions in Iceland in 1783 and 1784. Elgau, which was the next biggest one, which was in 860 and continued for about 6 years. The Holofernes eruption, which was 2014, 2015, and a lot of really beautiful places like the East Fjords, especially Mevatten and such. And so if people are potentially interested, and kind of want to gauge interest about whether or not people would be interested in basically having a student-like trip, but instead of camping all the time, we'd stay at hotels, would be a little bit easier instead of, yeah. Okay, so yeah, I'm interested to see if we have enough people to do a bus. This might be something to do next August. Be probably right after I finished my field campaign for Raven and right before, if we can manage it, the bigger field trip. So the idea for this is that can help support the field trip. So if people are interested, I've got a couple little cards here in the front. I'm happy to answer questions as well. But thank you so much, everybody, for coming out to the art show and being able to spend a little bit of time with me and with all the people here. And really appreciate you guys making the effort to come out.
Thank you.
Get the doors popped open here. There's still a few moments if you wanted to do your last art. Things open up back here. We're going to do the special viewing for the IRG folk. You guys know to come back, and then the public, everyone will be here at 6 p.m. Thank you again to Galileo Circle for punishing our alcohol and hors d'oeuvre. And yeah, Galileo Circle is the College of Science. So if you love science, donate to College of Science or donate to Galileo Circle. If you love LPL, you can donate on our UA Foundation page. If you love the art show, you can donate on the art show page. And if you love grad students, donate to this one. Yes, we love those field trips. It's really awesome. Because we can't always touch the planets, right? We have to do a lot of imagery. So it's really helpful for us to look at rocks. So yeah, we'll get the doors popped open in a few moments here. Any last questions for Christopher can come on down here and do one-on-one, and we'll hope to see you all again here this weekend. Thank you.
So there are a lot of where the magnet was. So the first time you're starting to get some signals is about 12 kilometers down. But you saw the actual magma is coming from about 17 kilometers down. But then as it started to get closer and closer to the surface, you could see there's a few kilometers long, a little dog leg at the end. And then the magma just kind of stalled out at a kilometer beneath the surface. It started going towards the southwest, and that's where we just went every day to be able to check the valley. 5 days after those first footages. And from the seismic tool, really critical tool. Yeah. Oh, no, it started when we arrived. There was absolutely no activity right now. Not a single earthquake, no indication that that's where an eruption was going to take place. People are always kind of betting which volcano might erupt, and that one I don't even think was on the betting chart. So then the earthquake started in February, and then started, so almost a month of seismicity before the eruption. But there were no before that, no clues. I just happened to be in Iceland and happened to be a volcanologist, so it ended up being a lot of fun.
Wow, talk about luck. Okay, well, thank you so much.
So you're measuring the biology associated with, are you using the chemistry of the underlying strata of the rock?
So there were people sampling the primary chemistry because you have to sample the active lava and quench it in water. So the overall chemistry was very, very consistent. But if you look at trace elements, you can always find details, and it's a little bit like reading the tea leaves in terms of what the trace elements we're talking about. Overall chemistry provided very clear information about what source depth it started at, how fast it was rising towards the surface, and people did a very clear chemical. There were two groups that were doing the chemical progression.